Hi everyone, today's lecture is going to be on stability with respect to how do we determine if a system is stable. Most of the time that we're going to be determining the stability of a system, that means that we're going to be dealing with the Laplace transform equation accordingly for the system. We're then going to see later on in this lecture that is a criterion known as the Routh-Hurwitz criterion that we'll be using with respect to these Laplace domain equations in order to determine the stability of the system. So any stable system basically is going to have a bounded input for any bounded output, or a bounded output for any bounded input. And as such, we're going to be assuming that we're dealing with single input, single output systems. We also know that once we have some Laplace domain equation, it's possible for us to get it into some partial fraction form and then perform the inverse Laplace transform to obtain a time domain equation. What we can observe here with respect to these time domain equations for this particular example is that for s plus 3 and s plus 2, we know that the roots here is going to be s equal to negative 3 and s equal to negative 2, which maps out equation equivalently to our exponent functions here being minus 3t and minus 2t. Because this is minus 3t and minus 2t here, this means that these exponents are stable decaying exponents. Now, if we observe our h of s equation here, and we factorize the denominator and find the poles accordingly, we basically can see that the poles of this equation here are going to be located on the left-hand side of the s-plane. And for any stable system, all the poles of that system must be on the left-hand side of the s-plane. If one pole is on the right-hand side of the s-plane, it basically means that this entire system is unstable. So for example, if we determine the poles of this g of s system here, even though they're going to be complex in nature, we can see that they basically are going to be on the left-hand side of the s-plane. And because they're on the left-hand side of the s-plane, that means that the system itself is stable. The pole zero plot that we're going to observe for this g of s system can be seen here. As we can see, all the poles here accordingly are on the left-hand side of the s-plane, meaning that they are less than s equal to 0. And as such, our system here is stable accordingly. So what happens when we decide to up how many poles are in the system? That means in such a case that we're going to have to figure out by trial or error, or if we're given a hint, what is going to be the first pole of our system, and then we're going to have to long divide and keep on going accordingly to figure out what are the other poles. So what happens if we decide to introduce some constant that may determine the stability of the system, such that we need to find a range fit? So this past paper question here from 2001 is what we're going to be attempted to solve within the next few slides in order to determine, okay, what is going to be the value of k for which the system is going to be stable for? And in answering the question, that means what is going to be the range of k for where the system is going to be unstable. But before we even do this, we need to determine what is going to be the closed loop transfer function accordingly for y of s divided by x of s, in order to determine our system transfer function. So we can basically calculate the transfer function, and then we can factorize the denominator and find the poles, and then look up the behavior of the poles with respect to k, and solve accordingly. But we want to come back to this in a little while. Our second way of doing this, instead of having to go that long way to find the poles and whatnot and so forth, is a way that helps as the system becomes more complex. Because in trying to find all the roots for more complex systems, this is going to end up being quite difficult. And the technique we're going to be using is referred to as the Routh-Hurwitz stability criterion. So the first thing that we do with respect to this is that we find the characteristic equation of the transfer function. So if you recall the basically transfer function here for our closed loop feedback system, where g of s is on the feed forward part and h of s is on the feedback part, if we find the transfer function here, we know that basically y of s is equal to g of s divided by 1 plus g of s h of s. And the characteristic equation is when we express the denominator of that transfer function being equivalent to 0. So as of such, 1 plus g of s h of s is going to be 0. And if we simplify that in some form, we're basically going to have some sort of polynomial equation going straight to 0. An example of this polynomial equation can be seen where our highest power here is s to the 4. And then we have descending powers of s, meaning that s to the 3, s squared, s1, s0, going all the way down, and we equate that entire thing to 0. Our second step is to tabulate the coefficients of the characteristic equation as follows. So we start with the even powers of s here, meaning that n here is going to be s to the 4. So this is going to be s to the 4 coefficient, s squared coefficient, and s0 coefficient. And then we go ahead on the next row of the table, being that they are the odd powers of s of n. Now, for instance, if the highest power of s in the characteristic equation was odd, we start with the odd powers first, and then we go with the even powers afterwards. So in accordance with our equation that we just now saw, in starting our Routh-Hurwitz table, the end result will end up looking like this for our starting point. So as we can see here, the highest power of s was s to the 4. So we start with s to the 4, meaning that we start with all even coefficients of s. So s to the 4, the coefficient here is 1. Then we look at s squared, our coefficient here is 3. And we look at s0, our coefficient here is 5. We then start with the odd powers of s for the next row. So s cubed, our coefficient here is 2. S to the power 1, our coefficient here is 4. And because there's no s to the power negative 1, our coefficient here is 0 accordingly. We then complete the rest of the table using the following equation as of such. This equation is known as polynomial theory, referred to as Sturm's theorem. So in finding for our next row of the equation, we basically say that we cross multiply using the lower left coefficient here. So we cross multiply here, and then we minus this cross multiplication, and we divide the entire result by this value here, in order to obtain this value accordingly. Well, it's time to solve for our next value with respect to the new row. We hold the first column coefficients constant, and we shift accordingly to the next column in order to obtain the new coefficient, in order to solve for our new value here. So as such, the cross multiplication still maintains the same form, so we cross multiply here, and then we minus this cross multiplication accordingly, and then we divide by this value here. This can be seen by this equation here accordingly as well. So if we map this out accordingly to our example equation, we can see that our s squared row will end up with these values here accordingly. To prove the point, 2 by 3 is 6, minus 4 is 2, and then divide by 2, we get 1. Then 2 by 5 here is 10, 0 by 1 is 0, so that means we still have a value of 10 here, and then we divide by 2, so we get our n value here as 5. We can keep on doing this accordingly for all further values, meaning that when we go to solve for the next row, being our s to the power 1 row, we then use the two coefficients on top of it accordingly as well. So we're no longer dealing with the top row here, we're now going down to the next row here. So for this coefficient, we use the two top values right above it, and then we also use the two values next to it accordingly in order to solve for this coefficient. For example, if we are solving for this coefficient here, we use these two values here, but then we shift this accordingly, so we use these two values here and so forth. So in solving for the entire table, our end result will end up looking like this. So this is what we refer to as our Routh-Hurwitz table. And then the stability criterion is what we're going to observe with respect to the values in the first column of the table here accordingly. Now, for stability, all the elements in the first column must be positive in order for the system to be stable. So all these coefficients here in the first column must be positive. If any one is negative, that means our system here is unstable. Our second criteria is that if there are any sign changes, meaning that the number of roots of the characteristic equation where positive real parts is equal to the number of changes in the sign in the first column of the array. So if there are any sign changes, we note these sign changes indicating how many poles are going to be on the right-hand side of the S-plane. So if we map this back to our Routh-Hurwitz table that we just calculated for our equation, we note that there's going to be a sign change from positive here to negative here. So that's our first sign change. And then the next sign change from negative here to positive here, meaning that there was a second sign change. So accordingly, that means because there are two sign changes in the first column, that means they're going to have two roots with positive real parts. So meaning that there's two roots or two poles that are going to be on the right-hand side of the S-plane. And because we had a sign change there, that means our system overall is unstable. Now, just to verify this, if you do plug in this equation into some solver online as of such, you're going to see that all the roots here for this equation, or all the poles, because it's a characteristic equation, is going to end up looking like this. As you can see here, for these two poles accordingly, they are more than s equal to 0. And as such, they're on the right-hand side of the S-plane. And once these poles exist on the right-hand side of the S-plane, the entire system is unstable. So that brings us to the end of Stability 1. Our next lecture for Stability 2 goes more in depth into the Routh-Hurwitz criterion. So I'll be discussing that more in detail and giving you more practice, as well as we're going to be answering the question that we saw earlier on in this lecture. Alright, that's it for today.